Hello, I'm Seema and welcome to part 8 of the chapter Redox Reactions. In this video, I'm going to tell you about the fractional oxidation numbers. But before I come to the fractional oxidation number, let us just remember what the oxidation number is. In a compound, you have different atoms, and these different atoms have different electronegativities. So when they are bound together, even by covalent bond, the one that is more electronegative has a tendency to pull the shared pair of electrons towards itself. And the one that is electropositive has a tendency to lose those electrons to the other atom, which is more electronegative. This loss does not completely take place. That is why it is a covalent bond. But due to these tendencies, the atoms appear to have a charge on them. And that apparent charge is represented by the oxidation number. For example, if you have hydrogen and oxygen in water, the hydrogen atoms are more electropositive while the oxygen atom is more electronegative. So oxygen has a tendency to pull the electron of both the hydrogens towards itself. So when the hydrogens kind of partially lose that electron to oxygen, each hydrogen appears to have a charge of +1, while the oxygen, which pulled the electrons of both the hydrogens towards itself, appears to have 2 extra electrons. Therefore, it appears to have a charge of -2. So we would say in water molecule, the apparent charge or the oxidation number of oxygen is 2, while the oxidation number or oxidation state of hydrogen is +1. And the oxidation number or oxidation state of oxygen is -2. So it has an apparent charge of -2. Now, having understood this, I told you about the different rules or different ways how we determine the oxidation state of an atom in a compound. And after having understood that, when we start studying more and more complex compounds, we come across compounds that are larger in size and that have the same atoms of the same element more than one time, or more atoms of the same element. And these atoms may be bound to the other atoms in different ways. And each atom appears to have a different oxidation state. And when this happens, you have, for every element, we assign an oxidation state. So for each atom of the same element, if there is a different oxidation state, so by convention what we do is, when we want to tell what is the oxidation state of that atom or the atoms of that element in that compound, we give an average of these oxidation states. Let us say there are 2 atoms who have an oxidation state of 3. And 1 atom which has an oxidation state of 2. So what will you do? 3 plus 3 is 6, plus 2 is 8. So the total number of oxidation states was 8. And out of those, there are these 8 oxidation states are being shown by 3 atoms of the element. So we say total is 8, 8 by 3 divided by 3. So 8 by 3 would be the average oxidation state. Now, this average oxidation state is a fraction. It is not a complete charge. And to even think that half an electron would move is impossible. So it seems a little confusing when you look at a fractional oxidation state, but whenever you see a fractional oxidation state, you must be clear that that particular element whose oxidation state is being talked about, there are more than one atom of it in the compound, and the atoms do not display, each atom does not display the identical oxidation state. They display different oxidation states, and that's why an average is given. And that is the reason why you are getting an average or a fractional oxidation state, which actually does not exist. And if you really see, even the concept of oxidation state itself is a conceptual concept. It is just imagined, because when we say it is the apparent charge, it doesn't mean the charge actually exists, right? So this is how I would explain the fractional oxidation states. So I have taken these examples as they are given in your NCERT textbook to understand the fractional oxidation state better. And what are the other conditions in which again you get fractional oxidation states, but it is kind of a little different from what we will be doing in the first three examples. The first example is Br3O8. This molecule is also known as tribromo-octa-oxide. Tri-bromo, 3 bromos, octa means 8, oxide means oxygen. So it has 8 oxygens and tribromo, 3 bromine atoms. This is the structure of this molecule. And when you look at the structure of the molecule, the oxidation number of bromine in this molecule is 16/3, which is fractional. In order to understand why it is 16/3, you must know the structure of the molecule. And if you know the structure of the molecule, what do you see? You see that this bromine is attached to 3 oxygens. This bromine is also attached to 3 oxygens by double bonds. And bromine in the center is attached only to 2 oxygens and 2 other bromines. Remember, when you have 2 atoms of the same element and they are combined with each other, none of them is more electronegative, because both of them have the same electronegativity, and therefore none of them would have an apparent charge with respect to the other. Both of them would be neutral. So whenever you have the atoms of the same element combined together, the oxidation number for that bond would be 0, because there would be no apparent charge. Both of them have the same charge. There will be no pull by any one of them. So whenever you have bromine attached to bromine, this bromine and this bromine, this bond is not polar, and therefore it is not contributing to the oxidation number. So 0, 0 here. But with oxygen, bromine with oxygen, oxygen is more electronegative. And therefore oxygen, except for peroxides, oxygen always has a charge of -2. So if you have 3 oxygens, so you have 3 oxygens means 3 minus 2 charges. So total number of negative charges is 6. If the total number of oxygens here is the negative charges is 6, and bromine with bromine is 0, it means this bromine is somehow neutralizing the 6 negative charges, and it can neutralize the 6 negative charges by having a positive 6 charge. So its oxidation state or oxidation number is +6. It is the same with this bromine, that it is attached to 3 oxygens, so -6 charge, balance it, 6, this would be +6. But the bromine in the center is attached to 2 bromines, so they are not contributing to the oxidation state at all. So 0 charge here, 0 charge here. But with the 2 oxygens, this oxygen and this oxygen, both of them have 2 negative charges each, which means 4 negative charges, and which are being balanced because this molecule is neutral. Since it is being balanced by this bromine should show an oxidation state of +4. So what do we notice in this molecule? That these 2 bromines have a charge of +6, while the bromine in the middle has a charge of +4. So what are the total number of positive charges that bromine bears, or charges that bromine bears? 6 plus 6 is 12, 12 plus 4 is 16, so 16 divided by how many bromine atoms? 3 bromine atoms, so the average is 16/3, and that is the average oxidation state in this molecule. And that is why we have a fractional oxidation state. Take the second example now. Here you have carbon suboxide. In carbon suboxide, this is the structure of the molecule. And if this is the structure of the molecule, what do we notice again? 3 carbons are attached to each other via double bonds, but the terminal carbons are attached to oxygens on the end. So if there is electronegativity difference, it can only arise between atoms that are of different elements. So you will have electronegativity here, you will have electronegativity difference here. But here, there is no electronegativity difference between the carbon-carbon bonds. So these are not contributing to the electronegativity or the oxidation number. Oxygen here, we know, has a charge of -2. Here also oxygen has a charge of -2. The entire molecule is neutral. Since the entire molecule is neutral, this carbon must be contributing +2, must be having an oxidation state of +2. This carbon also has an oxidation state of +2 because it has to nullify the effect of oxygen, which is -2. But this This carbon has a charge of 0 because it is attached only to 2 other carbon atoms. Identical atoms do not have an electronegativity difference, so it has an apparent charge of 0. Actually also its charge would be 0. So what is the total number of charges present on carbon? The total number of charges is 2 plus 2, 4 plus 0 is 4. But the number of atoms is 3. Therefore, the fractional oxidation number of carbon or oxidation state of carbon in this molecule would be 4 charges divided by 3. And they are positive charges. So do you understand? Again, we got a fractional oxidation state. Now the next compound here is, it is an ion. It is S4O6 2 negative. The compound could be Na2S4O6. That would be neutral. In that case, let us look at this ion first. S4O6 2 negative. The entire species has 2 negative charges. This is the structure. 4 sulfurs are linearly attached. Then to the terminal sulfurs, you have 3 oxygens attached to the terminal sulfurs, but one of the oxygens has a negative charge. The other 2 here are not negatively by double bonds and they are not negatively charged. It is the same here. So what do we notice now? Now we notice that to calculate the average, there are 4 sulfur atoms, and 2 of these, the oxidation states of these 2 would be 0, 0. And here, how many negative charges are there? Oxygen has a charge of -2, right? But this entire portion here, this oxygen has a charge of -1 even after the sulfur has neutralized it. Even after the sulfur has neutralized, it still has a charge of -1, which means the total number of negative charges of the oxygens would be 2 plus 2 plus 2 is 6. But 1 charge has not been neutralized. So how many charges have been neutralized by sulfur? Out of 6, 5 negative charges have been neutralized by sulfur. Therefore, in this sulfur is showing an oxidation state of +5, and it is nullifying or neutralizing the 5 negative charges of the 3 oxygens, but one of the negative charges of oxygen is not neutralized. Therefore, that remains as a negative charge here. The same is seen with this sulfur. This sulfur neutralizes 5 of the electrons of the 3 oxygens, but 1 electron is not neutralized. Therefore, this oxygen remains negatively charged. So if we had the compound Na2S4O6, the S4O6 2 negative would be the negative ion, and Na2, each sodium would have a positive charge. Both the sodiums could be present here by ionic bonding. This part has all covalent bonding, but the 2 sodiums and with the oxygens here would be ionic bond, and that would neutralize the charges on the 2 oxygens. But let us just forget about the sodiums here and see what would be the oxidation state or the oxidation number of sulfur that we would assign to this compound. The total number of sulfur atoms, 4. The total charge on sulfur atoms, 5 plus 5 is 10, because these 2 are 0. So 10 divided by 4, and 10 divided by 4 would be 2.5. So that is the oxidation state of sulfur. Now, we also find certain compounds which in nature are present as mixed oxides. Now, these mixed oxides are actually 2 different molecules in which the oxidation state of one of the atoms is different. The other atom, other than oxygen of course, is different. But yet, in every natural sample that you get, or every time you prepare this compound, you may find that it is formed in the same way, in the same ratio. I'll just give you an example. Fe3O4 is an example of a mixture of iron oxides, that is ferrous oxide and ferric oxide. This mixture of ferrous oxide and ferric oxide, FeO and Fe2O3, are actually 2 different molecules, yet they usually are present in the same ratio and are present together. So when you have a compound like Fe3, so what do? We just try to, for the sake of simplicity, we join the 2, because usually you will always find them in the same ratio. So we do not take individual molecules, we take them as a set, and we calculate its oxidation state, which also turns out to be fractional. Let us just see here. In Fe3O4, one iron atom, there are 3 iron atoms. One iron atom is combined with oxygen as FeO. So if it is combined with oxygen as FeO, oxygen has a charge of -2. So this iron will have a charge of +2 to neutralize this. Because on the whole it is a neutral molecule. If it was not, you would have seen a charge on it. It's not an ion. It's neutral. And it is not actually one molecule. So the other part of it is Fe2O3. In Fe2O3 there are 6 negative charges by oxygen and there are 2 irons. The 6 negative charges are being neutralized by 2 irons. So one iron is giving how many positive charges or how many electrons? One iron is giving 3 electrons. So the charge on iron here, each iron would be +3. So the oxidation state of iron in Fe2O3 is +3, but in FeO it is +2. But you have 3 atoms of iron when you're showing this combined molecule. When you're writing it in the combined form, you see there are 3 irons, 2 of which have a charge of +3 and 1 has a charge of +2. So how would you write? What would the average oxidation state be? +3, +3, +2. So 3 + 3 is 6, 6 + 2 is 8, and it is divided. How many iron atoms are there? 3 atoms. So it would be 8/3 would be the fractional oxidation state. But remember, this is not actually theoretically correct because this is not one molecule. It is a mixed oxide. Yet we try to simplify our work. We are lazy. Chemistry students are very lazy. We always find shortcuts. We find ways to write small formulae. We find equations because that gives you maximum information in minimum words. We are lazy. So this is another one example of our laziness. Since usually you find them in the same ratio, usually they are always present together. So let us call them one thing. That's what we've done here. Another example of mixed oxide is Mn3O4. And its name is very interesting. It is mangano-manganic oxide. Isn't it a cute name? Mangano-manganic oxide. Mangano-manganic oxide is actually a mixture of, again, MnO and Mn2O3. Very similar to FeO and Fe2O3. And its charge, the charge or the oxidation state of manganese in this case also would be the same, that is 8/3. Why? Let me explain it again. Oxygen is -2, so this manganese should have a charge of +2. And these 2 manganese, there are 3 oxygens, so 6 negative charges being supplied by 2 manganese atoms or being neutralized by 2 manganese atoms. Therefore, each manganese atom is neutralizing 3 charges. So its charge should be +3 of each manganese. So +3, 2 +3 charges and 1 +2 charge. Total number of charges is 8 and there are 3 atoms of manganese, so it is 8/3. The third example of mixed oxide is Pb3O4. It appears to be a very similar example, but in this case the formula is different of each oxide. Lead is also present in two different oxidation states. In this example, it is made up, or Pb3O4 is made up of PbO and PbO2. In PbO, oxygen is -2, so lead should have a charge of +2. And in PbO2, it is oxygen is -2 and there are 2 oxygens, so total number of negative charges would be -4. So this lead should have a charge of +4. So now, in this example, here you have 2 leads. So out of the 3 leads, 1 lead has a charge of +4 and 2 leads have a charge of +2, right? Sum it all up, 4 + 2 + 2 is 8. Total number of lead atoms, 3. Therefore, the fractional oxidation number of this also would be 8/3, right? Now these were examples of mixed oxides, which again have you write that the apparent charge is fractional and it is 8/3, but these are not actually the same as these, where you had the atoms of that same element in the same compound covalently bound, but here in mixed oxides they are different compounds which are just together, and for the sake of simplicity we are writing down their fractional oxidation states. Then comes sodium peroxide, another example. In sodium peroxide, I would like to calculate the oxidation state of oxygen. The reason being that we know that sodium always shows an oxidation state of +1. It does not show multiple oxidation states. But in a peroxide, we know that the charge on oxygen is different, and we can find the proof of it in this example. Na2O2 is the formula of sodium peroxide. The charge on sodium is 1 positive or +1, and there are 2 sodiums. So +1 into +1 is 2 positive charges. These 2 positive charges are being neutralized by the 2 oxygen atoms. So each oxygen should be neutralizing, should be having a charge of 1 negative or -1. Why? Because if it has a charge of -1, the 2 oxygen atoms would have a charge of -2, which would neutralize the +2 charge of the 2 sodiums. So from this example, we can see that in peroxides, the oxidation state of oxygen is -1, which is one of the rules that you take care of when you are assigning the oxidation number or the oxidation state. The 8th example here now is O2 positive. There are 2 atoms of oxygen and both of them are bound to each other. So what would the oxidation state be? The oxidation state would be 0. Why? Because whenever you have atoms of the same element, none of them is more electronegative than the other. So the 2 oxygens by themselves are not contributing to the oxidation state. But this is an ion, and it is an O2 positive ion. This entire species has a positive charge, and that positive charge has to be shared by both the oxygens. So both the oxygens are contributing to that positive charge. Therefore, for such an ion where you have atoms of the same element, but the entire species seems to have a charge, how would you assign the oxidation number to oxygen here? In O2 positive, there is 1 positive charge being contributed by 2 oxygen atoms. So if it is being contributed by 2 oxygen atoms, 1 oxygen atom is exhibiting a charge of +½ or +0.5. So that is the oxidation state of oxygen in O2 positive ion. Similarly, in O2 negative ion, what would be the oxidation state of oxygen here? Again, oxygen and oxygen, no electronegativity difference, but the entire species has a charge of -1. So each oxygen is contributing a charge of -½ half of that is being contributed by both the oxygens. Therefore, the oxidation state of oxygen in O2 minus would be -½ or -0.5. This is a very important topic for you to understand, because when you further, as you study chemistry and you come across these fractional oxidation states, your understanding of this topic will really come in handy. And that's the reason why I decided to cover this with you today. So if you found it helpful, give it a thumbs up, subscribe to my channel, recommend it to your friends, and please keep returning for more videos in chemistry. Thank you for watching, and bye-bye for now.